Before we get into translating hyperbolas off of the origin as the center, I wanted to just talk about the definition of a hyperbola, since we've talked about the definition of all the other conic sections. And so in green you can see I've written the definition of a hyperbola is the set of all points in a plane whose distances to the two fixed points in the plane, which are called the foci, those two fixed points, any point on the hyperbola will be created by this constant difference. So if you measure the distance from point 1, which I called P1 on my picture in black, if you measure that distance between point 1 and one of the focuses and point 1 and the other focus, then and you called one distance M and one distance N, that distance M minus that distance N, if you took the difference, and notice if you did this one, M minus N would turn out to be negative, so and distance can never be negative, which is why at the bottom I've written M minus N with absolute value bars around them, because it doesn't really matter which one's bigger and smaller, you just want the difference between them for the distance. That distance, or that difference, I mean, will be constant for any point that's on that hyperbola. So I used P1 in one example, I used P2 in another example, I used P3 as another example of points that are on the hyperbola. And if you measure that distance M and that distance N, and you subtract them, takes the absolute value to get rid of the negative, that will be constant for every single one of these points. And that goes on for infinity for any points that are on the hyperbola. So the hyperbola could be created by plotting every point that has a constant difference of M minus N, absolute value, and you can notice the M minus N distance for the green, and then you have an M and an N distance for the peach color, and an M minus N distance with the purple colors. All those amounts, when you do M minus N and take the absolute value, those amounts will all equal each other. It will remain constant, and that's called the constant difference. So that's the definition of hyperbola. It's not crucial to graphing hyperbolas, but it is good to know how a hyperbola is defined. So in our first example, you can see we now have an h and a k. Remember, it's x minus h, y minus k. By the way, the h is always next to the x, and the k is always next to the y. So when these flip-flop spots where the y is first and then the x is second, make sure that the k stays with the y and the h stays with the x. And then your center, in this case, will be 1, 3, always h and then k. And the formula already has x minus in it and y minus in it, so you use the positive versions of both of those, or the opposites. If it was plus 3, you would use negative 3 as your k. So we've got the center, and so we can graph that. We also have our a and b. And remember, it's not a being the bigger one, but a is always the first one. In this case, a happens to be the bigger one, but that is not why it's a. A is going to be the first one. And so a squared is 9, and that makes a 3. And we have b squared is 4, so b is 2. So let's graph what we have so far. First of all, you need to notice which direction to count your a and your b in. Since the a is under the x, you're going to count a in the x direction, which is sideways. And since b is under the y, you're going to count b in the up and down, or y direction. So let's plot that. Now that we have the points plotted, remember that the vertices are not always on the longer axis. The vertices are determined by what letter comes first. If the x comes first in the equation, then you know that x is the direction you're going to find the vertices. So these are the vertices, and again, not because they're a longer distance, but because they're in the x direction, which is the first letter. The other 2 points are not called co-vertices, so we're not going to label them as such, but what those do help us with is our box. Our box is going to consist of vertical and horizontal lines which connect or go through the 4 points that we have in a horizontal and vertical direction. So that creates our box. Our box is mostly important because it creates our asymptotes. And so we're going to do diagonals through the box, which make our asymptotes. And it always go through the center as well. And those are our asymptotes, which will guide our hyperbola. So we already know our hyperbola will come out of the vertices, which in this case are this direction, and it will hug our asymptotes but never cross over. So it will look something like the blue hyperbola that I'm drawing. But oftentimes they want more information listed than just that. If they just say graph, great, we're done. But if they want more information like transverse axis, conjugate axis, foci, and maybe labeling where the vertices are, then we're going to list those things below. Let's go ahead and find C so we can help to find the focus. Remember, in a hyperbola, the formula is c squared equals a squared plus b squared. And therefore, let's find C. When C doesn't come out rational, what you want to do, it's good to have both of these versions, the rounded off version and the exact version, because of how we're going to have to write the ordered pair versus how we're going to have to graph it. I like to use the rounded off version to help me graph where the foci are going to be. I'm going to count 3.6 units from the center, and it's always in the direction of the vertices. So the vertices are sideways this time, so our foci will also be sideways, and you're going to count 3.6 in either direction. So I've drawn the foci in green going 3.6 in either direction from the center. Then what the radical form is useful for is they usually don't want you to write the ordered pair in a rounded off format. They'd rather have the exact format. And so when we're listing where the foci are located as coordinates, they would prefer the exact version, which includes the radical, rather than the rounded off version. And it's really hard to see where exactly it is as a number. So what we do is we just label it as the center plus square root of 13 and the center minus square root of 13. And so the center, you can see, is 1, 3. The 3 up will not change, so both of these will have 3 in the Y spot, because it's 3 up on both foci. But the sideways you'll write as a combination of the center, which is 1, plus the square root of 13, because that's where it would be located. It would be 1 over to get to the center, and then another square root of 13 over to get to this focus. Then, to go backwards, we'll do 1 starting at the center minus square root of 13, and that puts us at the other foci. And so that's how you label your x value of your focus. It'll just be 1 plus square root of 13 and 1 minus square root of 13. And that's how you label your coordinates if you're asked for them. Oftentimes you're also asked for the vertex, and the vertex on this picture, since it's a nice number and it lands right on a corner of your grid box, you can just count and see where it is. And so one of them is at 4, 3, which is the one to the right. The vertex to the left is at -2, 3. But kind of like we did with the focus, if that wasn't a nice number, if A was not a nice 3, we would just add the number A to the H part of our center, just like we did for the focus. So if the number is not nice, you can always add and subtract the A value, whatever that not nice A value might be. You can add and subtract that to the H. Now this is if it's a sideways parabola. If it was an up and down parabola, you'd be adding the A value to the K. You'd also be adding and subtracting the A value to the C value from the K, not the H. But you'll know that just by looking at the picture. That's why I always like to graph the picture and then determine where the coordinates are. Also, you may be asked the length of the transverse axis, and remember the transverse axis connects the vertices, so we're talking about this purple distance here. And again, if it's not a nice number, you'll just double A or write 2 times the square root of something. But in this case, A is nice, so 2 times 3 is just 6. And then the conjugate axis will always come from 2 times B, and in this case it is 4. But you can also see that from the picture that the conjugate axis is this direction, up and down, and that distance is 4 if you just count it on the graph. So it kind of just depends if it's a nice number or an irrational number as to whether you can just count on the graph or if you actually have to put something plus the square root of something or something times the square root of something. So that is the length of our transverse axis and our conjugate axis. The last thing they might ask you is the equations of the lines of the asymptotes. And so that's a y equals mx plus b, but oftentimes they'll only ask you, once they move it off of the center being at the origin, they oftentimes won't ask you the equation, they'll just ask you for the slope of the asymptotes, and if that's the case, it's a little bit easier. The slope of the asymptotes in this case are, remember, it's just rise over run, so I always start at the center and go out to one of the corners, and always work left to right. So the left point is the center and the right point is that corner up there. So to get one of these red lines, this red line right here, the slope is rise of 2 and run of 3. And so that's a 2 over 3 rise over run slope. And so if that's all they ask for, great. That's the slope of one of your lines. Your other line, you'll go from the center out to the bottom corner, and that rise is -2, and the run is still to the right 3. And so you're going to have slopes of positive and negative 2/3. Now, that's the slope of this line is -2/3. Now, if they ask you for the equation of the line, you also have to have a b, which is your y-intercept, so you'd have to have y equals mx plus b. And that'll take a little more work, but I'll show you how you could do it in case you're asked that question. So the equation of a line is y equals mx plus b, and I'm going to do this line here, the one that has the negative slope, and you just want to find a point that line goes through. Any point that line goes through. I'm going to choose the center because I can see it goes right through the center, and the center was 1, 3. And so you can choose any point. The center might be the easiest one, but you can choose any point on that red dotted line. And so what I'm going to do is I'm going to put in 3 for my y. I'm going to put in the negative slope that I found a minute ago. And then I'm going to put in the x, which is 1. And then the only thing that's missing is b. So now we can find b. So if I end up adding 2/3 to both sides, I end up with 11/3 is equal to b. And so I can write my equation for this negative sloped line, which is this line right here, the red one, and it is y, we'll go generic on our x and y now, to represent all the x's and y's on the line, and then we'll put in our slope of -2/3, our generic x, and then plus 11/3. So that is the equation of the negative sloped line. I can put in all the same kind of stuff into the other one and get the equation of my other line, which I'll do here. So the next time through, we are trying to find the equation of this line, which has the positive slope. We can use the same center point, 1, 3. We put in positive 2/3 as our slope. 2/3 times 1 is 2/3. Subtract that from both sides, and you get 7/3 for b. And so our equation is y equals positive 2/3 x plus 7/3. And in red, we have the two equations of the asymptotes.